Statically determinate means stiff, almost rigid, can find forces independent of deflections, strength independent of stiffness. Statically indeterminate, all systems need both force and deflection to carry out the calculations. So remember, that's how statically determinate and statically indeterminate systems work. So you have to get to the stage where you could do both of them. Okay, at this stage we are here. This is a SD system, so things are nice. SI systems are a problem. Statically indeterminate systems are a problem. I mean, problem meaning you have to do more. Statically determinate systems, it's easy. Okay, so now that we got that, so how do we do a force analysis? Remember, the two structures or two objects of the same material can be compared through stress. What I mean by that is, I don't compare the forces, but I compare force per unit area. Why is that? Because I told you that forces, the failure forces, the forces required to break the system scales with the area for ideal specimens. Okay, force required to break will approximately scale with area for ideal systems. What I mean by that is, if I have 1 centimeter squared and it fails at 2000 newtons, a 2 centimeter squared system will fail at 4000 newtons. That's why what we do is we look at stress. In our case, stress in bar BC the tensile bar is FBC divided by cross-sectional area of BC, which is 2308. How much was it? 2309. So let us make it 2310. In fact, we don't have that kind of accuracy. It's only 2300, but it's okay. 2300 newtons divided by area. So now you can see, by choosing the angle, we figure out the length of BC. By choosing the area, we now can figure out the dimension. So I have to pick some area. So how much can we pick? Let's say I pick, example, how big do you want it to be? So, if you think it's 1 meter squared, that's a gigantic cable, right? Look at that cable for the crane. It was pretty thin, agreed? So we're going to try a small area. Let us try 1 centimeter squared. That's about this much. That's the cross-sectional area. That's a pretty big beam, it's a solid bar. So if I pick 1 centimeter squared for the cross-section, that is equal to 100 millimeters squared. Because 1 centimeter is 10 millimeters. Okay. So what's the stress? Sigma is 2310 divided by 100, which is 23 Newton per millimeter squared. That's called a megapascal. So you need a material. So if you make a bar which is 1 centimeter squared in cross section, you need a material that will withstand 23 megapascals of load. Let us see if we can find such a material. So let's see what's a typical material look like. So I have a nice graph for a lot of different materials. Sorry, I got to scan it like that. There you go. So now it's time for us to look at this one. So I'm going to expand this out a little bit so that you can take a look. See, this is the nice thing about Excel. We can do calculations, everything on the same setup. So you don't have to look at different things. I hope you can see this graph. Oops. We are right now not focused on the deflection, so I don't care about the x-axis. I don't really care about the x-axis. I'm just looking at the y-axis. And what matters is where it cuts this one. We have assumed that the bar is almost rigid, right? That means we are assuming hardly any deflection, right? If there is no deflection, how much force can it stand without any deflection? So let us pick something. Let us say 1020 steel. That's a commonly available steel. So you go back, 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 you go back. Let's see. Goes like that. There you go. It's out there. Okay, I'm sorry, that's 1020 steel. And you say its yield strength is here in megapascals. That's about 95 megapascals. Hey, you got plenty of reason to be happy because you only wanted 23 megapascals. You had 95 megapascals. If you look at aluminum, you can see it's about 1010 aluminum is about 50 megapascals. If you pick very high quality, very high strength steel, which is this cold rolled steel, for example, and that's 600 megapascals, and you're saying, I don't need that. So if I pick 1020 steel, that's pretty nice, 95 megapascals. If I make it out of aluminum, it's about 50 megapascals. Both of them are okay. So I could do like an aluminum bar. The nice thing about aluminum bar is that it won't rust and it's very light. The nasty thing about it is it doesn't like to be oscillated. So if you're going to put it in a windy location, probably aluminum bar is not so great. But indoors, this, that, and the other, you could get away with doing aluminum. At this stage, at this stage of evaluation. Okay, so that's how we decide. So let's say I decide to pick 1020 steel. So I'm going to go up here, and we can now play a lot of what if games. Where was all my calculations? Yeah, there's my calculation. So I'm going to play some what if type of situations. So I'm going to, and this is where we really want cross-sectional area. I'm going to pick 100 millimeter squared. So stress is 100 is FBC divided by equals that divided by that. Okay, so now I can pick yield strength, material type. So let us say I pick 1020 steel. Yield strength turned out to be 95 megapascals. So how much the ratio between this number and that number, how much is the actual load versus maximum load? So this is called factor of safety. So safety factor equal to allowed load divided by design load, allowed stress divided by design stress, which turns out to be equals that divided by that, and so you got a safety factor of 4. That's a high safety factor, and you can think, hey,